Okay, boys. Good morning. In our yesterday's class, we completed structural isomerism in complex compounds. Today, here we are going to discuss geometrical isomerism and optical isomerism in complexes. Geometrical isomerism, optical isomerism. These two are collectively taken as that is spatial isomerism or stereo isomerism. Listen carefully. This is my revision class only. Please careful. My dear, we have two types of complexes. That is coordination number 4 and coordination number 6. Already yesterday I told you, coordination number 4, it has two types of hybridizations. One is sp3 hybridization with strong ligand, mostly. It is with weak ligand. dsp2 hybridization with strong ligands. If sp3 hybridization is there, that is tetrahedral shape. dsp2 hybridization is there, that is square planar. Square planar. Tetrahedral means there is a central metal atom or ion. It has 4 ligands. Those 4 ligands are in tetrahedral shape. It is a 3-dimensional 3D picture. This is ligand, this is ligand, this is ligand, this is ligand, 4 ligands tetrahedrally arranged. Okay, so all these are not in the same plane. So here, geometrical isomerism not possible. Tetrahedral complexes, geometrical isomerism is not possible because these are not planar. If planar is there, that only geometrical isomerism. There only geometrical isomerism is possible. But here, geometrical isomerism not possible. But in square planar, there is metal, ligand, 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 and ligand. All these are in the same plane. Whenever all are in the same plane, there geometrical isomerism possible. Geometrical isomerism possible. That means in coordination number 4, in square planar complexes, we can explain geometrical isomerism. Okay, here optical isomerism not possible. But here optical isomerism possible. Coordination tetrahedral complexes exhibit optical isomerism. Square planar complexes exhibit geometrical isomerism. So these two are nothing but stereo isomers. So calculate total number of stereo isomers means combination of both geometrical and optical isomers. Okay, stereo isomerism. Stereo isomerism. So particularly in coordination number 6, here also two types of hybridizations possible. One is D2 sp3 hybridization, sp3 D2 hybridization. D2 sp3 hybridization, this is with strong ligand, this is with weak ligands. So in these two cases, geometrical isomerism possible. Most of the cases when it is possible, I will explain it. Optical isomerism also possible. Geometrical isomerism, optical isomerism, both are possible. So first of all, let us discuss coordination number 6 complexes, geometrical isomerism. Coordination number 6 complexes, geometrical isomerism. See here. So if it is a sp3 D2 or D2 sp3, that is both are octahedral in shape. Octahedral shape is like this. Metal, ligand, 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 ligand. These are 4 ligands within the plane. Okay, 1 ligand above, 1 ligand below. It is coordination number 6, my dear. Okay. Let us numbering all these ligands as it is the first ligand, second, third, fourth, fifth, and sixth. Total 6 ligands are there. Okay. See, my dear. Let us take it is within the plane. Metal is here. 4 ligands as a square. 1 ligand above and 1 ligand below. Okay. The above ligands with all these 4 ligands which are at the corners of the square planar are at the same distance or not? Tell me, my dear. This ligand, Shivanarya,
Yes, sir.
this ligand is at the same distance with the corners of the square ligands.
Same distance.
Same distance or not?
Same, sir.
This position with these 4 positions, same distance any, that is cis type any. So that means this position with these 4 positions, square planar positions, are cis. Now down the down ligand any. This ligand, bottom ligand with this square planar ligands, same distance or not?
Yes, sir.
Yes. Now this ligand with these 4 positions, cis position. See, my dear, this position and this position both are in the same side or not? These 2 positions in the square planar, same side or not? Respond. Okay. So cis position. These 2 are in the same position, same plane, same side or not?
Same, sir.
Cis position. These 2 are cis positions. These 2 are cis positions. Now identify these 2.
Trans.
Same side or opposite side?
Opposite.
Opposite side. Trans. These 2.
Opposite.
Opposite. Above and below.
Opposite.
Opposite. That means in octahedral, what are cis positions? What are trans positions? Let us assume, my dear. First position, first ligand with 2. Cis or trans? Tell me. First ligand with 2. There are 2, 3, 4, 5 within the plane. 1 is above the plane, 6 is below the plane. 1 and 2 positions. Cis positions or not? Yes. 1 and 3, 1 and 4, 1 and 5. All are cis positions or not?
Yes, sir.
Next, like that. 2 and 6, 3 and 6, 4 and 6, 5 and 6. Cis positions or not? Bottom with bottom ligands.
Yes, sir.
Okay. Next. 2 and 3 cis. Same side. 3 and 4 cis. 4 and 5 cis. 2 and 5 also cis. Correct or wrong?
Yes, sir.
Positions. All those are cis positions. Next. Transpositions. Transpositions. 1 and 6 trans. Correct or wrong? Above ligand and below ligand. Both are in opposite. 1 and 6 trans. 2 and 4 trans. Correct? 2 and 4. These 2 are opposite. Next. 5 and 3 also trans. Only 3 trans positions, boys. Remaining all are in the 6 positions. You can memorize those trans positions. Trans positions are nothing but opposite sides. Okay. So 1, 6 positions are opposite, 2, 4 opposite, 3, 5 opposite. Remaining all are cis conditions. Okay. Now let us assume different ligands. Some are monodentate ligands, some are bidentate ligands. We can discuss here. Okay. So cis positions, trans positions are possible or not possible. Let us take with simple examples. See here. See, my dear. That is See here, I'm taking cobalt NH3 6 times plus 3 iron. CO NH3 6 times plus 3. See, my dear, this complex, it is a coordinate number 6 complex. That means 6 coordinate covalent bonds are there around that cobalt plus 3 iron. Coordination number 6. That means it is octahedral complex. I am discussing only now octahedral complexes. See here. Coordination number 6. All these ligands are same type. That is why I am taking it is M L 6 types. All are same types. Same ligands. Okay. ML6. That means all ligands are same. Or ligand I am treated as A. All ligands are A types ligands. So that means here is metal A, 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 A. These are in the same plane. One A above, one B, one A below. My dear, is there any cis trans you can distinguish of the cis and trans? Possible or not possible? Check once.
Not possible, sir.
Not possible. That means here cis trans isomerism possible or not possible? Because no one is cis, no one is trans, because all ligands are same.
Yes, sir.
Here cis trans isomerism not exists. That means in this complex, cis trans isomerism not exists. Okay, now cis trans isomerism is nothing but geometrical isomerism. If one of them is replaced with another ligand B, for example, CO NH3 5 times Cl plus 2 iron. 5 ligands one type, one ligand another type. 5 ligands one type, another ligand. Okay, 2 types of ligands are there. Check once again. So here, cis trans are possible or not possible? Not possible. Check. Here, these two, all A's are in cis positions. There is no B to identify. Okay. Here also cis trans isomerism not possible. MA5B, not possible any.
Yes, sir.
Okay. One more A is replaced with B, my dear. One more A is replaced with B. Now it is MA4BT. Nothing much. CO NH3 4 times Cl2 plus. Okay, na? Did you understand?
Yes, sir.
So CO NH3. Now it is, these are 2 chlorines, these are 4 ammonia, this is cobalt. See, my dear, both the B atoms we can identify along with B only. Only you should consider B. Both the B's are on the same side or opposite side?
Same thing. Opposite
Huh?
side. The both are
Opposite side. That means it is the cis or trans.
trans.
Trans. Now it is a trans isomer. That means here is possible. Next, similarly, see here. M, A, 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 B, B, A. These are cis and trans. Now identify both the B's are in the same side or opposite side. Cis positions are not positions.
Cis.
Is this cis? Cis, because planar positions along with about below the plane are cis. Now it is a cis positioning. It is trans positioning. Now is this cis trans exhibit or not exhibit?
Yes, sir. Exhibits.
Exhibit. So number of times asked, which of the following exhibits is trans isomerism? Which of the following exhibit geometrical isomerism? Like that. You can check the situations. Okay. And most important, now 3 atoms, 3 ligands are same type and 3 ligands are another type. For example, cobalt, NH3 3 times, Cl3. Okay, it is special type, my dear. This can also exhibit cis trans isomerism. MA3B3. MA3. What type of isomerism? This is geometrical isomerism possible. That is particularly facial and meridional. Facial, that is what face and mer isomers are possible. Facial meridional isomers are nothing but geometrical isomers. Facial meridional isomers are nothing but geometrical isomers. Okay, legenda. Boys,
Yes, sir.
facial and meridional isomers are geometrical isomers. See here, what is that? Metal, 4 positions are within the plane, 2 positions above and below the plane. Okay. Now 3A's and 3B's. I'm writing A's at these positions. A and D. B, B, B. Okay, na? A, B, B, B. Now check. A covers one face, one triangular position. Correct or wrong?
Yes, sir.
So that is called as facial position. That is called as facial. Okay. Or see here. Or see here. Just a minute. Just a minute. It is within the plane angle. Now I'm writing one more. Is this a place? Is this a face, my dear? Is this red triangle a face or not for a octahedral?
Yes, sir.
No, it is not a face. Because check here, it is within the plane, 1 point above. From here is a triangular position is possible. Correct or wrong?
Yes, sir.
Here to here, a triangular position is possible. Correct na?
Correct. Yes,
This triangle is a face. Like that, to above the ligand from the square planar situations. So 4 faces, 4 triangular faces are available. Correct or wrong?
yes, sir.
1, 2, 3, 4. 4 faces. Just like that, bottom also 4 faces. And how many faces actually exist?
8, no. 4.
8. That is why it is octahedral. 8 faces are there. Above 4, below 4 triangular faces. Is this among those 8? Is this among those 8?
Yes, sir.
Is this triangle among those 8 faces or not?
Yes, sir.
Check once. What are those faces? Which is with above and below the ligands, triangular positions are triangular planes are available. Triangular. Is this plane a face
No, sir.
or not?
No, sir. No, sir.
Huh?
No, sir.
Listen. One more. No, don't confuse that. I'm taking M. I'm taking A here, B here. Okay, now identify A. Now identify that face. Now identify this one. It is within the plane triangular body. Now among these two, which is a face for our octahedron?
Sir,
In
B.
first case or second case?
Second case.
Second case.
Second
That
case.
is why this is called as a facial isomer. This is called as a meridional isomer. Okay, na?
Yes, sir.
So facial and meridional both are cis-trans isomers. Facial and meridional both are cis-trans isomers. Like this, easy or difficult to find out whether the given complex exhibit cis-trans isomerism or not? Easy na?
Yes, sir.
Arya? No one, no Arya. Next. Shiva, this is very important. Facial and meridional, A3, B3. Exhibit geometrical isomerism, that is facial and meridional, a special type of geometrical isomerism. Okay?
Okay, sir.
Now, M, A, B, C, D, E, F. That means all the ligands are different and that exhibits geometrical isomerism. Clear up? Please remember that point. M, A, B, C, D, E, F. All monodentate ligands are different. That can also exhibit geometrical isomerism. Clear? No doubt. No doubt. Next. My dear, here I am taking only monodentate ligands, but let us take some bidentate ligands. Okay. See here. CO, En thrice. CO, En thrice. With plus 3n. En means ethylene diamine. Ethylene diamine means CH2, CH2, NH2, NH2. Here, this is donor atom, this is donor atom. Both the donor atoms are same type. That is why this is, we call it as metal AA2 plus 2 plus 3n. AA2 plus n or something else. That means both the donor atoms are same. Both the donor atoms are same. Okay, now.
Yes, sir.
So this is, I'm writing this one as metal. These are the positions. My dear, any bidentate ligand, it is a bidentate ligand, always join at cis positions only. That means A and A are first ligand, only at cis positions. That means A and A cis position, A and A cis position. These are the three ligands. These are the three ligands. See, my dear, metal, A and A, these two A, this is the ligand. Those are at cis position or trans position, or same single
Trans,
ligand. Trans. This type of linkage is not possible. That means both the donor atoms of a single ligand are only at cis positions acceptable. Don't at trans positions. Okay, na? That means this type of arrangement is possible, but not that type of arrangement.
yes, sir.
Okay, so
Okay, sir.
this is acceptable. Only at cis positions, those two donor atoms are possible. Now I'm taking, this is cis isomer, my dear. This is cis isomer. It has no trans isomer. Is this symmetrical or unsymmetrical? Check.
Geometrical.
Unbalanced or balanced? See here two types. Here only one type. Is this
Yes, sir.
balanced structure or unbalanced structure?
Imbalances.
Unbalanced structure. That is, it is unsymmetrical structure.
Yes, sir.
Okay.
Yes, sir.
So any unsymmetrical complex exhibit optical isomerism. That means
Yes.
no doubt, bidentate complexes with at least one bidentate ligand exhibit optical isomerism. But we are in geometrical isomerism. It has only cis form. It has no trans form. Okay. It has no trans form. For example, M A B twice C2, my dear. What is the coordination number of this complex? Here AB means it is a bidentate ligand, but both the donor atoms are different. Here both
Yes,
the
sir.
donor atoms are same. Here both the donor atoms are different. That means overall from this side
6.
4 plus 2. Total coordination number is 6. I am writing like this. Metal metal. See, it is A, it is B of the bidentate ligand. It is A, it is B of the bidentate ligand. Okay. It is C, it is C. Okay. So both the C's are in the same side or opposite side? Both C's. Here we can explain the concept along with C and only with C. Both the C's are in the same side or opposite side? Shiva. That is in opposite side. It is a trans angle. Trans angle. Now here, I'm taking this is B, this is A. This is complete trans. Both the A's are in opposite, both the B's are in opposite, both the C's are in opposite. It is a fully transformed. Fully transformed. Like this, cis-trans isomerism is explained with coordinate number 6 complexes. So with monodentate, with bidentate, bidentate with symmetry, that is both the donor atoms are same, both the donor atoms are opposite, that is different. Okay. So
Yes.
like this, you can identify different complexes, whether it is possible or not possible. Okay, now.
Yes, sir.
So M, A, B, C, D, E, F exhibit geometrical isomerism. Our total 15 geometrical isomers are possible in 15. Okay, 15
Yes.
geometrical isomers are possible. Next, that is coordination number 4 complexes, my dear. Just I completed coordination number 6. You can try with different examples. I will send the notes. Okay.
Okay, sir.
Coordination number 4 means metal, A, 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 A. Square planar complexes. Already you know which is cis, which is trans. All these atoms are, that is M, L, A, that is M, A, 4 type complex. It is. No one is cis, no one is trans. It has no cis trans isomerism. M, A, 3, B. That is A, B end. Here also only one B ending. It is not possible to explain whether it is cis or trans. It has no cis trans isomerism. Next, M, A2, B2, my dear. Just already I wrote. So both the A's are in opposite. It is a trans end. If both the A's are in the same side, M, A, A, B, B. Okay. So both the A's are in the same side. Now it is a cis form. That means here M, A2, B2 exhibit cis trans isomerism. Correct or wrong? M, A2, B2 exhibit cis trans isomerism. Next, M, A2, BC, different ligands. Both the A's are on the same side. It is cis. Both A's are opposite side, trans. Here cis trans isomerism possible. Cis trans isomerism possible. Next, M, A, B, C, D. Just like M, A, B, C, D, E, F. Here also M, A, B, C, D. Here also cis trans isomerism possibility. In your textbook, it has 2 cis forms, 1 trans form, and total 3 geometrical isomers possible. M,
Good
A, B,
morning,
C,
sir.
D.
Sir,
Yes,
Anubhav
good
here.
morning.
Sir, my
M,
internet
A, B,
just came back. I
okay.
was not able
M,
to.
A, B, C, D type complex. M, A, B, C, D type complex. Cis trans isomerism possible, but it has 2 cis positions, 1 trans position. How is that? See, my dear. With B, A is ciscend and C also ciscend. D is transcend. Like that, you
Yes, sir.
can arrange everything. It has 2 cis forms, 1 transform exists. That is the number of times asked with it. M, A, B, C, D type. That is square planar complexes. That is platinum, Cl, Br, I, and yeah. These are the different complexes. This is the combination. Here platinum plus minus 2. For this complex, how many cis trans isomers are possible or how many geometrical isomers are possible? It is M, A, B, C, D type complex. It is like this. It has 2 cis forms, 1 trans form. Total 3 geometrical isomers are possible. Like that, you should count. Okay. So similarly, just before we completed with the bidentate ligand, here also you can decide cis trans isomerism. So this is cis trans isomerism idea. Next one, optical isomerism. optical isomerism. That means there is a substance through this plane polarized light is passed. This is already in your organic chemistry training. This is our complex. Through this complex, plane polarized light is passed. It may penetrate directly, or something little bend is there, or this type of bending, that is clockwise rotating, anti-clockwise rotating, or slightly they may move. That light is transmitted. If it is slightly moved, it is optically inactive. If it is bent along, that is either clockwise or anti-clockwise direction, those are optically active. Optically active. If it is in if this complex rotates plane polarized light towards clockwise direction, that is dextro rotation. It is anti-clockwise direction, that is levo rotation. This type of rotation possible if in the complexes. If a complex can rotate either if the complex rotates plane polarized light either in clockwise direction or in anti-clockwise direction, that complex seems to be no doubt optically active substance. If cannot rotate, that is optically inactive. Optically inactive. Now, note those complexes. So with coordination number 4 and coordination number 6. Coordination number 4 and coordination number 6. That is in coordination number 4. M, A, B, C, D type complex exhibits optical isomerism. Particularly, my dear, so it is a tetrahedral complexes exhibit optical isomerism. Here, octahedral complexes exhibit optical isomerism. In tetrahedral complexes, M, A, B, C, D type complexes exhibit this optical isomerism. In octahedral complexes, no doubt, M, A, B, C, D, E exhibit optical isomerism. Along that, a complex having at least one bidentate ligand, either with symmetric ligand or unsymmetric ligands. At least one bidentate ligand, both are same donor atoms, or both are different donor atoms in a particular ligand. No doubt, at least one, and I explained here, a metal having at least one bidentate ligand. No doubt, 95% complexes are optically active. At least one, my dear. Now see here, CO oxalate 3 times plus 3. Sorry, minus 3. Is this complex exhibit optical isomerism or not? So it is oxalated. Oxalate a bidentate ligand. Already I told to you, at least one bidentate ligand, it is optically active. It is optically active. That means optical activity is nothing but it can rotate plane polarized light either clockwise direction or anti-clockwise direction. So bidentate ligands can rotate it because their unsymmetry exists. Asymmetry exists. So their plane polarized light automatically rotated. So that's why presence of at least one bidentate ligand with symmetric or unsymmetric ligands. Both the donor atoms are same or different, whatever it may be. That complex exhibits optical isomerism. Please keep that one in your mind. Complexes having at least one bidentate ligand exhibit optical. Which are the following exhibit optical isomerism? Number of questions are coming out in your objective side. There, set is the given complexes having at least one bidentate ligand. Automatically, that should be exhibit optical isomerism. If no bidentate ligand, so M, A, B, C, D, E, F, and M, A, B, C, D both can exhibit optical isomerism. Okay, now.
Yes, sir.
So
Yes,
this is
sir.
simple topic, and please be conscious about the existence of availability of at least one bidentate ligand. At least one bidentate ligand. So some other examples also there. Okay, but in our syllabus these are like this. I'm discussing only along NCERT part of it. Okay. So this is isomerism topic, my dear. In your complexes. This is isomerism topic. Now, let us identify what type of hybridization is there. That is VBT, valency bond theory. Valency bond theory, VBT in complexes. This VBT explains hybridization in the complexes, paramagnetic property is the given complex is magnetic or non-magnetic, and shapes of the molecules and magnetic properties are clearly explained by VBT. You should identify what type of hybridations exist in that particular complexes, in your given complexes. Based on that, whether the complex is octahedral, tetrahedral, or square planar. What type of hybridization? Is this sp3 or dsp2 or sp3d2 or d2sp3? We can identify along only with VBT. It is very, 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 very important. Okay. Valency bond
Yes,
theory.
sir.
VBT. I'll see here. Here, hybridization you can identify. Hybridization. How is that? See here. I'm taking an example, my dear. Here, we can decide the complex that is ligands as strong ligands and weak ligands. So that is very, very important. For that purpose, in your textbook, in CFT topic, a series of arrangement of different ligands are given to you based on their strength. Okay. That series you should by heart. That is called as spectrochemical series. With that spectrochemical series, we can decide whether the given complex is whether the given ligand is strong ligand or weak ligand. We can decide with the spectrochemical series. Do you know?
I minus less than
Spectrochemical series. This is order of strength of ligands, my dear. Tell me.
I minus
I minus less than
Br minus
Br minus less than
thiocyanide SCN
SCN, thiocyanide,
Cl minus
CNS,
so sulfide ion
S minus 2,
F minus
F minus,
OH minus
OH minus,
oxalato 2 minus
oxalato, OX minus 2 minus,
H2O
H2O,
NCS minus
NCS minus,
ethylene diamine tetraacetate EDTA.
S, EDTA,
Yes, yes.
EDTA,
4 minus
4 minus,
NH3
NH3,
EN
less than, EN, less than,
CN and CO, most powerful
CN, CN, yes,
carbonyl.
CN minus less than CO.
CO.
This is as per your NCRT. This is as per your NCRT. See, my dear, here there is water in here. Okay, water. Before water, all those ligands, up to these ligands, these are considered as weak ligands. Up to water, all those ligands are weak ligands. Please be conscious. What are those? Our halogen ions. Please keep in mind. Halide ions are strong ligands or weak ligands? Halide ions are strong ligands or weak ligands? Tell me.
Weak, sir.
Weak ligands. See, my dear. Here, donor atoms are oxygen. Here, donor atom is oxygen. Here, donor atom is oxygen. Here, donor atom sulfur. Here, donor atom sulfur. That means oxygen donor atoms and sulfur donor atoms are also weak. Am I correct or wrong?
Yes, sir.
If donor atom is oxygen, see, my dear, if donor atom is high electronegative elements, then the ligands is weak. Why it is weak? Because it is high
Because
electronegative element, it has not that much stability tendency to donate that electron pair to others because it has high electronegativity. It is not ready to give that electron pair to others. So the species which is ready to give electron pair to others is the best ligand. But these are not best ligands. That is why these are we consider as weak ligands. Okay, na?
Yes,
Clear?
sir.
Okay. So if donor atom in the ligand is high electronegative element, then it should be weak. That is the way to identify, to memorize whether the given ligand is strong ligand or weak ligand. All halogens are weak ligands. If oxygen is the donor atom, weak ligand. If sulfur is the donor atom, weak ligand. Clear?
Yes, sir.
Yes, sir.
Now, where is ammonia? Ammonia is here actually. Ammonia also there. No, here. Allied with roads. Okay. Now, next chance. What is the order of electronegativity, my dear? Order of electronegativity. Nothing but mostly halogens greater than, oxygen greater than, nitrogen greater than carbon, like that. Okay, na? Clear? This is the order of electronegativity.
Yes, sir.
So sulfur also here is there. These are high electronegative elements. Generally, if these are the donor atoms, that is weak ligands. If these are the donor atoms, that is strong ligands. Those are strong ligands. Clear? Here, NCS, nitrogen is the donor
Yes,
atom.
sir.
Here, EDTA, nitrogen is the donor atom. Already I wrote, check once. Nitrogen is the donor atom. Here also, nitrogen is the donor atom. So, these are all nitrogen donor atoms. Correct?
Yes, sir.
All those are nitrogen donor atoms. These two are carbon donor atoms. Okay. Now, strength of the ligand is if donor atoms are carbon greater than, nitrogen greater than, then oxygen greater than halogen, my dear. Is this correct? Strength of the ligand. Carbon donor
Yes,
atoms
sir.
are
Correct.
strong ligands. Carbon donor atoms are strong ligands. Nitrogen donor ligands are something little bit weak than carbon. This is the order it. Okay.
Yes, sir.
Please keep in mind at least like this, based on donor atoms. Okay. At least like this. Carbon donor atom ligands are strong. Nitrogen donor atoms are second base. Oxygen donor atoms are third base. Halogens are weak ligands. Okay. Oxygen and halogen ligands are
Yes, sir.
weak ligands. Nitrogen and carbon ligands are strong ligands. So no need to all total series cell. So just I'm trying to explain for this one. So I'm writing this one only. Okay.
Yes, sir.
Now it is the basic for VBT. You should identify whether the given complex is stronger, whether the given ligand is strong ligand or weak ligand. That is very, very important to explain this VBT, my dear. Okay. So now, is there any doubt whether the given complex is strong, whether the given
No, sir,
ligand
no
is
doubt.
strong or weak? So that is Shiva.
Yes, sir. No doubt.
Okay. Now, see here. Let us take an example. CONH3 6 times plus 3, my dear. Now, what type of hybridization is here in CO complex? Okay. First of all, decide here what is the ligand? Ammonia is the ligand. Is this ammonia ligand strong or weak? Decide.
Yes, sir.
Ammonia
Strong.
ligand. Donor atom is
Yes, sir.
nitrogen. Is the ligand strong or weak?
Strong ligand.
Strong ligand. strong ligand. How many ligands are there? 6 ligands. It is a monodentate ligand. Okay, here coordination number is equal to 6. Up to now, am I correct? Okay.
Yes, sir.
Now, what is the oxidation state of cobalt here? Oxidation state of cobalt is here. So calculate. I want to find out oxidation state. Let it be 8
+3.
plus 6 ammonia. Each ammonia has 0 and is equal to +3, my dear. Therefore, X is equal to +3. Therefore, oxidation state of cobalt is +3. Clear? In this complex, the oxidation state of cobalt, central metal atom, that is cobalt, has +3 oxidation state. Okay. Now, let us
Yes, sir.
assume about cobalt. Cobalt atomic number 27, my dear. 27 means its outermost electronic configuration D7S2 only. S2. It is 27 means S2D7. It is the shortest way to write the electronic configuration. It is 4S2, it is 3D7. Okay, na? 27 means S2D7. 26 means S2D6. 28 means S2D8. Like that. S is 4S, D is 3D. So I'm just adjusting D7S2 only. It is 3D7, 4S2. Okay, 3D7. But here cobalt is in cobalt +3 format. That means 3 electrons are lost. Always first electrons lost from S. If it is insufficient, then from D and E, it is overall 6 S0. Now in cobalt +3, 3D6, 4S0 is the configuration. Okay, 3D6. It is 3D, 4S, it is 4P, it is 4. You should write always all these orbitals, 3D, 4S, 4P, 4D. Okay, now 3D contains how many electrons? 6 electrons. 1, 2, 3, 4, 5, 6. 4S0, 4P0, 3D0. Now decide, my dear. Is the given ligand is strong ligand or weak ligand? The ammonia is strong ligand or weak ligand? Strong ligand. See, my dear, these d orbitals we can split 3 and 2 under. These are T2Z orbitals, these are EZ orbitals. Later I will explain what are those 2TZ and AZ, that is in CFT. Okay, CFT I will explain the T2Z and EZ. So first of all those 5 orbitals break down into 3 and 2. Okay. Those electrons which are present in 3D level are not paired up. Not paired up. That means not against to the Hooke's rule. But because of presence of this strong ligand, these easy electrons are coming into the D2Z electrons. Now all the unpaired electrons are paired or not?
Yes, sir.
Why these 2 unpaired electrons are paired up? Because of presence of strong ligand. If it is weak ligand, the structure is like this only. If it is, for example,
Okay, sir.
if it is weak ligand, the structure, that is the electronic configuration only like this side, no change. But presence of strong ligand, these easy electrons entered into the T2G. Entered into the T2G. Okay, at this position, is there any unpaired electron or not? It is in the presence of ligand or in the absence of ligand? Is this in the presence of ligand or in the absence of ligand?
Sir, this is in the presence of a strong ligand.
Yes, it is the presence of weak ligand. Sorry, strong ligand.
Strong.
Is this has any unpaired electron?
No,
Is this
sir.
has any unpaired electron?
No,
No, no unpaired electron. That's why it is diamagnetic.
Diamagnetic.
Diamagnetic. Now, how many ligands are there? 6 ligands. That is coordination number 6 here.
Yes.
So we can choose 6 empty orbitals from the starting one. It is 1, 2, 3, 4, 5, 6. Yes. 5, 6. That is 2 3D orbitals. It is 3D orbitals. 1 4s orbital. 3 4p orbitals. That is why 3D orbitals are used. That's why it is a D2sp3 affiliation. If 4D orbitals are used, that is sp3d2. That means inner d orbitals are used. That's why it is inner sphere complex, inner orbital complex. If outer orbitals are used, outer d orbitals are used, there is outer orbital complex. Okay, na? So now it is inner orbital
Okay, sir.
complex or outer orbital complex. If 3D orbitals are used for hybridization, that is inner orbital complexes. If
Inner,
4D
sir.
orbitals are used, that is outer orbital complexes. Now the given example is inner orbital complex or outer orbital complex.
Inner.
Inner orbital complex. Okay, now what type of hybridization is this? It is a D2 sp3 only.
D2
So
sp3.
sp3 D2 or D2 sp3, that should be octahedral case. Now this complex is octahedral. Is there any unpaired electron in the final case?
No, sir.
No unpaired electron. That means number of unpaired electrons n is equal to 0, my dear. Therefore, magnetic moment mu is equal to under root n into n plus 2 Bohr magnetons. It is a spin only formula, most important formula to find out the magnetic moment. So n is equal to 0 means mu is equal to 0. It has no magnetic property. It is a diamagnetic component. It is a diamagnetic. Clear? So hybridization
Yes, sir.
identified, structure identified, magnetic property also identified. Magnetic property also identified. Okay. Now, my dear, see, there are some exceptions. Note down these exceptions. What are those exceptions? With CO plus 3. Actually, water is weak ligand or strong ligand? Tell me. Actually, water is weak ligand or strong ligand?
Sir,
Yeah, donor
weak.
atom is also. Okay. Actually, it is weak ligand, but with CO plus 3, this water acts as strong ligand. Keep this in your mind. Did you write?
Yes, sir.
Not. Okay, now with the CO plus 3, water is strong ligand, not weak ligand. Just like ammonia. Ammonia here, that means if CO plus 3, here ammonia, in place of ammonia, if water is also replaced, the hybridization is D2sp3 only, not sp3d2. Okay, now. Shiva, identified.
Yes, sir.
Yes, sir.
With CO plus 3, water actually weak ligand, but with CO plus 3, water is considered strong ligand. Therefore, CO H2O 6 times plus 3 complex is D2sp3 hybridized or sp3d2 hybridized? Tell me, my dear.
D2
This
sp3.
is with
D2
this
sp3.
is with strong ligand. This is with weak ligand. Here water strong ligand or weak ligand with CO plus 3 condition.
Strong.
Strong. That's why this is the hybridization. This is not. That means this is the hybridization here. CO H2O times the complex is D2sp3. Clear?
Yes, sir.
Yes.
Next, point number 2. With CO plus 2, ammonia. Is ammonia strong ligand or weak ligand actually?
Strong.
Strong. Correct? Actually, it is a strong ligand. But with CO plus 2, this behaves like weak ligand. With CO plus 2, ammonia is a weak ligand. Please remember.
Okay, sir.
Clear? If with CO plus 3, ammonia is strong. But with CO plus 2, ammonia is weak ligand. With CO plus 2, ammonia is a weak ligand. Clear?
Yes, sir.
Noted down or not? Next.
Done, sir.
Now, ethylene diamine also. It is not ethylene diamine. Oxalated, OX. Oxalate. No, my dear, it is sufficient for us. So with CO plus 2, ammonia is weak ligand. Ammonia is weak ligand. Next.
Okay, sir.
Next. Just a minute. With point number 3. With Ni plus 4. With Ni plus 4. All weak ligands behaves like strong ligands. Okay, now with Ni plus 4, all weak ligands behaves like strong ligands. Very, very, very important. With Ni plus 4, all weak ligands are strong ligands. Okay, now
Halogens also.
clear? NiCl4N. Here nickel is in plus 4 oxide state. Override is 0, my dear. Here chlorine, strong ligand or weak ligand?
So it's weak ligand, but it will convert to strong.
But with Ni plus 2, it should be strong ligand.
Yes.
Okay. Next
Okay.
and most important. Next and most. If it is fourth point, it is third point. Now fourth point, my dear. If the metal is 4D or 5D series element. If our central metal ion is cobalt in place of cobalt, cobalt is a 3D series element. So 4D or 5D series elements are there. If our metal atom is or metal ion is 4D, 5D, all ligands are strong ligands. Clear?
Yes, sir.
With 4D, 5D metals, every ligand should be strong ligand because of high nuclear charge. 4D, 5D elements have high nuclear charge, effective nuclear charge is more. Because of that, every ligand, whether it is strong or weak, whatever it may be, it should be strong. Okay, that is platinum, my dear. 3D series element or 4D series element or 5D series element. Is this 3D or not 3D element? It is not.
Sir,
It is not a
4D
3D element. It is not a 3D element, first of all.
5D
Okay,
element.
that's enough for us. That is enough for us.
Okay.
Okay, so now for this chlorine. Chlorine is strong ligand or weak ligand?
So it's strong ligand for platinum.
So see, palladium Cl4 minus 2, my dear. Here chlorine acts as strong ligand or weak ligand?
Strong, sir.
Strong. Okay, now clear? That means with 4D, 5D metals, all ligands are strong ligands. Based on that, you can decide hybridization. If strong ligands are there, pairing of electrons takes place. If weak ligands are there, pairing of electrons not takes place. Okay, like that. So I will continue the concept tomorrow with some more examples. Right now, I'm stopping here.